The University of Alaska Anchorage is proud to submit our critical design review video for consideration by the URC Judges Panel. UAA Robotics took on this challenge for its inaugural year with the support of many local donors and professional organizations. Special thanks goes out to Dean Barlow at our College of Engineering, ASME Alaska Chapter, Beaded Stream, SAME, Schlumberger, Crescent Electric, Alaska Industrial Hardware, Linden, and many private donors.
We initiated our project by developing a requirements traceability matrix. This helped our design team quickly build consensus around design choices, such as the primary material selection of 6061 aluminum, chosen for its strength-to-weight ratio, availability, and cost. We are also able to take advantage of co-located fabrication facilities and personnel which have allowed us to meet an aggressive design timeline. By intimately involving club members in all aspects of rover design, fabrication, and testing, we are able to quickly and effectively overcome all failures that arise over the course of this project.
Preliminary chassis design requirements centered on the extreme retrieval challenge. The suspension assembly was designed for 16 inches of chassis clearance with another 8 inches of differential wheel positioning to traverse rough terrain. Our selection of brushless DC hub motors balances speed with torque requirements while also contributing to a low center of gravity, which provides stability on steep slopes.
The rover is controlled using a pair of gamepad controllers in conjunction with a custom-developed graphical user interface. Communication with the rover utilizes a pair of Ubiquiti radios operating over 2.4 GHz. With these radios, we're able to transmit multiple video streams and data over 2 miles with limited interference from terrain obstruction. By transmitting 4 camera streams, our operators have maximum visibility for driving and operating the arm. Budget limitations prevented our team from using LiDAR methods for autonomous navigation during this inaugural attempt. This led us to use a stereoscopic camera instead. Thus, our autonomous navigation algorithm utilizes computer vision to analyze the terrain for obstacles and targets when in proximity to GPS waypoints. Because we are a new team with limited institutional resources, this challenge required some of the most creative solutions developed for this rover.
Our 6-axis, 16-kilogram robotic arm meets our requirements for all the University Rover Challenge tasks. After an iterative design process, we settled on a design consisting of a swivel base, 2 linear actuators for the shoulder and elbow joints, and 2 wrist motors for manipulating an end effector. Our arm is capable of lifting 8 kilograms and has a reach of 1 meter on 3 sides of the rover. It can move at a speed of 1 meter per second with a 5mm fidelity at its end.
Our end effector design was centered around simplicity and task requirements. The 2 pincers are capable of 2.5 inches of travel and are driven by 3 NEMA 17 stepper motors, allowing for precise control down to 5mm. The wrist has a 6-axis range of motion, allowing for anthropomorphic movements. 2 rubber contact pads allow for the end effector to securely grasp a variety of geometrically complicated objects. The end effector has 2 attachments. A soil extractor can penetrate topsoil found in the competition environment for the science cache task. Additionally, an extension can rotate a DIN nut for equipment maintenance.
Extensive research led to our strategy for completion of the science cache task. 3 sensors for reading barometric pressure, temperature, and relative soil humidity will accompany our soil extractor on the rover. Images from a rotating camera will be stitched together to provide high-quality panoramic pictures of each sample site, while another mounted on the arm will provide close-ups. Our off-site science experiment suite will be conducted using chemical dyes that react with biological macromolecules to indicate the presence or absence thereof. We'll be testing for monosaccharides, polysaccharides, lipids, and proteins, all of which are required for life to inhabit the soil. These tests were chosen for their simplicity, efficiency, and cost.
This concludes our 2017 URC Critical Design Review submittal. We appreciate your consideration and look forward to seeing you at the Mars Desert Research Laboratory.